we're doing things a little bit differently. So right now I'm sharing my screen in PowerPoint. I tried this out last night and it seems to work a little bit better. Um, and it allows me to write, which we've got problem solving to do. And that is really better done with writing versus typing. So you can see how you'll actually be writing it out and what the answers are going to look like. So this is a mole-to-mole calculation. This is what we were doing last time. How many moles of mercury 2 oxide were decomposed to yield 0.764 moles of oxygen gas? So you always want to start with rephrasing the question. What we have is 0.764 moles of oxygen gas. And what we want to know is how many moles of mercury 2 oxide will we make? So I like this, I like using PowerPoint better too because I can actually keep the stuff that I write on previous slides. Uh-oh. Yes, I am. Raise your hand if you can hear me. Okay. So some people are having issues. Let me see if I can respond to the chat. Okay. Thank you for raising your hand and letting me know. All right. So this is the question that we have. 0.764 moles of oxygen. How much mercury 2 oxide was decomposed to make that oxygen gas? The first thing that we have to do is figure out our mole-to-mole ratio, or our mole ratio. And what we said last time is that for our unknown, that's going to go on the top of our mole ratio. So we're going to look to the equation and see how many moles of mercury 2 oxide there are. There's 2 moles, so that's what we write down for the top of our mole ratio. The bottom is going to have information about our given. We're given information about oxygen, so we're going to go to the balanced equation and write down the coefficient for the oxygen gas, and that's 1. Now we have to set up the equation. I abbreviate equation EQN. We're going to take 0.764 moles of oxygen gas. We're going to multiply by our mole ratio, which you said is 2 moles of mercury 2 oxide for every 1 mole of oxygen gas. When you do that multiplication, you're going to just take 0.764 and multiply by 2, divide by 1. You should get 1.53 moles of mercury 2 oxide. So, raise your hand if that was like, still don't really get that. If you still feel like you need some help in understanding the mole-to-mole ratio. Or you can say yes or me. You can write it in the chat. So are we okay with this? I need y'all to say something. Okay. Thank you, Brianna. All right, because everything that we're doing from now forward is going to involve using the mole to mole calculation. So if you don't understand this part, then it's going to be a struggle bus for the rest of the lecture. So we're continuing chapter 9. We're doing more stoichiometry, which is also called chemical equation calculation. Stoichiometry is using the relationships of a balanced chemical equation to carry out calculations. So we've been doing the mole to mole, but we can actually do other types of problems that will give us information that's a little bit more useful in terms of doing an experiment. The three main types of problems that we're going to focus on are mass-to-mass stoichiometry problems, where you're given an amount of grams of some substance and you need to turn that into grams of another substance. The second type is mass to volume, where you're given a mass and you have to convert that to a volume in liters or milliliters of another substance. And the final type is volume to volume, where you're taking liters or milliliters of one gas and converting that to milliliters or liters of another. These problem types are the calculations that you use to determine the theoretical yield in percent yield problems. So remember, we did percent yield is equal to the actual yield, which is what you do in the experiment, the result, over the theoretical yield, and you multiply that by 100%. The calculations that we're doing will give us the theoretical yield. So I could pair one of these problem types with a percent yield question to say, you're given this amount of substance, what mass of substance X will be made, and then part B would be, you actually obtained this many grams, what's the percent yield? So that's where we're going with this. First, we're going to talk about mass-to-mass problems. And there's a lot of text on this page, and I'm leaving it up because it can be helpful. I'm going to post this PowerPoint. I'm going to save all of my writing and stuff on it and post this to Blackboard in addition to posting the video. So if you don't catch something in your notes, you can look at this or you can look at the video on YouTube. But this is telling you the 3 steps that you're going to do for a mass-to-mass stoichiometry problem. You're always going to be given the mass of a reactant or product and asked to figure out the mass of an unknown reactant or product. And the steps are always the same. So this should be on your problem-solving cheat sheet, like the one that you should have started for chapter 8, where we did, atoms to moles or atoms to grams, that sort of thing. Add this to your cheat sheet. So this is mass-to-mass stoichiometry problem. You're going to start off with your mass of your given. And that's always in grams. You're going to convert that to moles of your given. Now here's your pop quiz. When you're trying to go from mass to moles, what do you need to use? This is something we talked about in chapter 8. What do you need to use? What unit factor do we need to go from mass to moles? And if you're like, I don't know, you can say, I don't know. We need grams. Molar mass. The two Camerons combined. With your powers combined, you got the right answer. So for this, we need molar mass. So that first step, you're going to need your molar mass of the given. Once you have your moles of given, you're going to convert that to moles of your unknown. Now, we just did a problem like this. What do we need to go from moles of one thing to moles of another using a balanced chemical equation? What is that called? Not Avogadro's number. That's going from atoms or molecules to moles. We need to go from moles to moles. It's what we used in that do now problem, to go from moles of oxygen to moles of mercury 2 oxide. There's a name for that. It's got mole in the name. It's a hint. Oh, we crickets this morning. All right. Mole ratio. You need a mole ratio to go from moles of one thing to moles of another using a balanced chemical equation. So we got to remember the terminology. Otherwise, it's going to be a struggle bar. So far, we've gone from the mass of our given in grams to moles of our given using the molar mass. Then we go from moles of our given to moles of our unknown using a mole ratio that we determine from the chemical equation. The final step is to go from moles of your unknown to your mass of unknown. And that's going to get us back to grams. We're going to use another molar mass. This time, it's the molar mass of the unknown substance. So you'll be using two molar masses, and you'll need to keep that straight. But this is the plan for every single mass-to-mass problem. If you can identify the problem type, then you know what your plan is, and then you set everything in accordingly. All right? So we're going to do an example of this where we put this plan to work. So keep up. I'm going to be asking you questions along the way, and I want you to help me solve this. What is the mass of mercury produced from the decomposition of 1.25 grams of orange mercury 2 oxide? And we have the molar mass of mercury 2 oxide is 216.59 grams per mole. So that's nice. We don't have to calculate that molar mass. We said that our first step is going to be going from our grams of given to moles of given. But before we even get there, we know this is a mass-to-mass problem, but how do you identify it? What is the mass? So there's one mass, okay, that's grams. And our given information is also in grams. So if you see two pieces of information, the question and the given information, you see what units those are in, that will tell you what type of problem. It's asking for a mass, and you're given a mass. So that means it has to be a mass-to-mass problem. Once you identify that, then you know which plan to put into place. We're given information about mercury 2 oxide. That's this over here. So I will label that as given. What we need information on is the mercury. That's our unknown. Now we can keep those two things straight. The first part, we need to go from grams of mercury oxide, mercury 2 oxide, to moles of mercury 2 oxide using the molar mass. Now the molar mass is given in this problem, but you will not always be given molar mass. So let's go ahead and write that part out. We're starting with 1.25 grams of mercury 2 oxide. If I want to get rid of grams, should the grams go in the top or the bottom? Don't everybody answer at once. Sure, I can repeat that. If we need to get rid of grams, do we need to put grams on the top or the bottom? There we go. I was like, yeah, I should get this one. Right, it should go on the bottom. So we're going to take our molar mass of 216.59 grams HGO, put that on the bottom. That means that the 1 mole HGO goes on the top. So that's part 1. The second part, we have to go from moles of mercury 2 oxide to moles of mercury. What do we need to use to convert from moles of a given to moles of an unknown? I just gave you the hint before. It's something that has to do with moles. Not percent yield. That was something we talked about, but it's not percent yield. Mole ratio. We need our mole ratio. Our unknown is what goes at the top. So we look at the balanced equation for our unknown. How many moles are there? There's 2 moles of mercury in our balanced equation. That's what goes at the top of our mole ratio. The given moles goes at the bottom. That's 2 moles of mercury 2 oxide. That's the mole ratio that we're going to use. Okay. So we can take a second and recap. The goal of what we're trying to do is figure out if we decompose 1.25 grams of mercury 2 oxide. So let me use a laser pointer here. So we're given 1.25 grams of this, the mercury 2 oxide. And the question is, how much mercury will we make from that? The first thing we have to do is figure out how many moles of mercury 2 oxide we have to begin with. So for that, we use the molar mass of mercury 2 oxide. So we take our grams and we multiply by the unit factor of 1 mole of HGO over 216.59 grams. That will get us to moles of mercury 2 oxide. The next thing we have to do is figure out how many moles of mercury we can make from that number of moles of mercury 2 oxide. For that, we have to get a mole ratio from the balanced equation. For every 2 moles of mercury that you make, you're going to need to have 2 moles of mercury 2 oxide. That's what this mole ratio says. And that's what the equation says. If you have 2 moles of mercury 2 oxide, you're going to make 2 moles of mercury and 1 mole of oxygen gas. So we're using the relationship between the mercury 2 oxide and the mercury to figure out how many moles of mercury we're going to make. Does that help, Cameron? Okay. One more part. So now we're in moles of mercury. But the question is asking about grams, so we can't just leave it there. To take moles of mercury and convert it to grams of mercury, what do we need? How do we go from moles to grams? Molar mass of mercury. Exactly right, Cameron. So we're doing like the reverse of step 1. We're taking moles and going to grams. So we need the molar mass of mercury. For that, you go to your periodic table, because mercury is an element. So you take the atomic mass from the periodic table and express it as grams per mole. So in this case, my periodic table says 200.592 grams per mole. So that's our molar mass. We want grams at the end of this. So where should I put grams, the top or the bottom? We have a vote for bottom. Any other votes? Keyshawn says top. Uh-oh. It should go in the top. We're not trying to cancel anything out, and we can't cancel that out. We're trying to cancel out moles. So 1 mole of mercury should go at the bottom, and our grams of mercury should go at the top. So hopefully the different colors help you see the different steps. The first thing that we did was go from grams to moles of HGO. And you can see that if you go through and do your canceling, so I'm going to use red to cancel. We get rid of the grams and we're left with moles. So that first step checks out. The next step, we're trying to go from moles of mercury 2 oxide to moles of mercury. When we look at the mass, we can cancel out the moles of mercury 2 oxide because there's one on the top and one on the bottom. The only way you can cancel. So that's a check. We're now in moles of mercury. We need to get that to grams of mercury. We cancel out our moles because there's one on the top and one on the bottom. and the units we're left with at the end is grams of mercury. When you put this into your calculator, which I want you to try, you're going to take 1.25 divided by 216.59, multiply by 2 and divide by 2, which is the same thing as, 1. And then you're going to multiply by 200.592. Give that a try on your calculator and let me know what you get. Give me 3 sig figs. I don't want all them numbers. Give me 3 significant figures. Yes. So you should get 1.16 grams of mercury. Don't forget about the units. You need to tell me grams and grams of what. So on your homework and on the next exam, you need to have units. If you don't have units, you're going to lose a point. So make sure that you have units there. This is grams of mercury. So how did that feel? One, I want to know how this is working out because I'm doing a little bit different process to share my screen in PowerPoint and write. So do you think that this is working out better? Is everybody able to see things okay? Yes. Because this feels better for me too. My handwriting doesn't look crazy. Yeah, I like colors. When we were in class together, I had all the colors for the board. So this makes me happier, and I think with all the math we have to do, this is going to be better. So for those of you that joined a little bit later, I'm using PowerPoint and I'm sharing my screen. So all of these annotations will stay, and I can save this, and I'm going to post it to Blackboard along with the video on YouTube. So you'll have both as resources for when you're doing your homework and studying. All right, so that's a mass to mass problem. You're converting one mass to another. Oops, I put 2 in there just in case. I didn't know if I'd have enough room. The next problem type that we're going to go over is mass to volume. Now I'm going to introduce these problem types. I'm going to give you the homework to try. Yeah, so I'm trying to give you all the resources. And honestly, what you need to do is when you're doing your homework, identify the type of problem and then go to that part of the PowerPoint or the video, whichever one helps you the most, and then copy it down. Josh, did you raise your hand on purpose? You can always just write your question in the chat. So we'll go over these types, have your cheat sheet for the different problem types and how to identify them, and then use the plan and go through it step by step. So match up the steps that I'm doing and apply it to the problem that you're doing for homework. So you'll have one mass to mass problem, and then you'll have one mass to volume or volume to mass. So the same thing, just steps in reverse. So now we're going to go over mass to volume. With mass to volume, you're given a mass of a reactant or product, and you have to figure out a volume. When we talk about volume, automatically think about a gas. So we're talking about liters or milliliters of gas at STP. So remember that standard temperature and pressure. If you see a question and you see the words volume, gas, liters or milliliters, you see STP, that clues you in that one of the things you're dealing with is going to be a volume. So you're going to deal with volume and then either mass or another volume, which we'll get to that probably next class. There are 3 steps, just like before, and I'm going to break them down a similar way. What we're given is a mass. So you're going to take that mass of your given, which is in grams, and convert that to moles. If you have a question, you can just type it in the chat. I think sometimes people are raising their hand by accident. But if you have a question, I'm all ears. Or all eyes, because all people don't use their voice, but that's fine. How do we go from the mass of something to moles of something? I'm going to keep asking this until everybody gets it. How do we go from mass to moles? Molar mass, thank you. So you're going to need a molar mass. Next, you're going to take your moles of given and convert that to your moles of unknown. You should see a trend here because these are the same 2 steps as the mass to mass problem. So from moles of given to moles of unknown, what do we need to convert? Mole ratio. Yes. So we need a mole ratio from the balanced equation. It may be frustrating to be like, why do you keep asking the same question? Because y'all ain't answering like you know it. So until you do, I'm going to keep asking. The final step is the new step. So we're going from moles of unknown to volume of unknown. This, we're going to use something else. So instead of molar mass, we have to use molar volume. And this was from chapter 8, where we said that 1 mole of gas at STP has a volume of 22.4 liters. So that is molar volume. That's how you go from mole of gas to volume of gas. And pay attention to whether or not the question is asking for liters or milliliters. So the overall, what we do for mass to volume is you take your mass of given, convert that to moles of given using molar mass. Convert your moles of given to moles of unknown using your mole ratio from the balanced equation. You take your moles of unknown and convert to volume of unknown, which better be a gas, using molar volume. Now let's walk through how to do that. First thing, identify the problem type. Now I told you this is a mass to volume problem, but if you're reading this problem without a title on a slide, you need to be able to identify it. How many liters? That's the question. Okay? Question mark liters, hydrogen, so hydrogen gas, are produced from the reaction of 0.165 grams of metal. So we have grams of metal. That sure looks like a mass. And it says that it's happening at STP with dilute hydrochloric acid. You have a given mass, and you're asked about a volume. So that means that it has to be a mass to volume question. Don't skip that step of identifying the type of question you have, because if you skip it, you may not do the final conversion properly. The first step is always going from mass to mole. So we've got grams of aluminum, and we need to get to moles of aluminum. And I'll label here with the reaction our given, which was the aluminum, and our unknown, the hydrogen gas. Look at your periodic table and tell me what the molar mass of aluminum is. Yes. So we'll put 26.98 grams per mole. Don't skip the step of writing out your plan and gathering all your information, because this makes putting the equation together a lot easier. So that's going to be our first step down here. We have 0.165 grams of aluminum. Am I putting grams in the top or the bottom? Grams are going to go on the bottom. Because whatever we're trying to cancel, it needs to be opposite. We're trying to cancel grams, so they need to go on the bottom. And that leaves the 1 mole of aluminum for the top. Because remember, this molar mass, what it looks like is like this. That's how you write it as a unit factor. The grams on top, moles on the bottom, or you could put moles on top and grams on the bottom. Our second step is going to be taking the moles of aluminum and converting that to moles of hydrogen gas, which is our unknown. And we're going to use a mole ratio for that. We're trying to get rid of the moles of aluminum. So should that go on the top or the bottom? Is the mole ratio where people are still getting lost? Okay, so we have a vote for top. Any other votes? All right, we have another top. So this time, actually, it goes in the bottom because we're trying to get rid of the moles of aluminum and convert to moles of hydrogen gas. So we're actually going to go to the balanced equation, and we see that there's 2 moles of aluminum in the balanced equation, and that's going to go at the bottom. See how there's 1 mole of aluminum at the top, and then we have moles of aluminum down at the bottom? Those two are going to cancel, and that's what we want. At the top, we're going to put the number of moles that we have in the balanced equation of hydrogen gas. That's 3 moles of hydrogen gas. Does everybody understand that? Because the mole ratio part, that's the key. If you don't have the right mole ratio, then you're not going to get the rest of the problem right. So raise your hand if you need me to go over that again. Okay. So we can go over that again. What we're trying to do is go from moles of aluminum to moles of hydrogen gas. That means we need a mole ratio from the balanced equation. In the balanced equation, there's 2 moles of aluminum for every 3 moles of hydrogen gas produced. So those are the 2 numbers that we're going to need, 2 moles of aluminum and 3 moles of hydrogen gas. But the question is, which one goes on the top and which one goes on the bottom? We're trying to get to the number of moles of hydrogen gas. We're trying to get rid of moles of aluminum. We've already got moles of aluminum as our unit here because we converted from grams to moles of aluminum. Now we need to cancel out those moles and leave our unit in moles of hydrogen. We have moles in the top for aluminum, so we have to put moles in the bottom for aluminum in order to cancel it out. Does that help a little bit more? And I can show you we get rid of grams, we get rid of the mole, and now we're left with moles of hydrogen gas. Does that help? You're welcome. We've still got one more part to do. We have moles of hydrogen gas, but the question is asking for a volume. How many liters? To go from moles of hydrogen gas at STP to liters of hydrogen gas, we're going to use molar volume. And again, that's 1 mole of gas has a volume of 22.4 liters at STP. we need to write that as a unit factor. We need to get rid of moles of hydrogen gas so that we're left with liters. The liters will go on the top, and the moles of gas will go on the bottom. And when you continue on with your unit analysis, you're going to get rid of those moles of hydrogen gas, and you're left with liters of hydrogen gas. Try putting that into your calculator and see what you get. And don't forget to give me units. Don't be shy. Yep, so there should be 3 sig figs, but with 2 sig figs, that's right. I would give you credit for that. You had your units. I'm not going to be too much of a stickler for significant figures. I mean, don't give me 5 when you should only be giving 2, and don't give me 1 when you could give me 4. But you should get 0.205 liters of hydrogen gas. We have time to go through one more problem, and that's going to be the reverse of this, going from volume to mass. But it's going to be the same thing, just literally in reverse. Are there questions on this one? It's one of those things you got to practice and let it sink in. All right. So this time we have a volume to mass problem. It is the exact opposite of mass to volume. This time we're asked how many grams of sodium chlorate, so that's a question mark grams, which is a mass, are needed to produce 9.21 liters of oxygen gas at STP. That's a volume, and it's given. So that means this is a volume to mass question. Your given information is a volume. Your question is about a mass. Now let's go ahead and label that on our equation. So how many grams of sodium chlorate? Sodium chlorate is over here, the reactant. That's our unknown. Our given information is about oxygen gas. The first step, which actually I'm going to try to be super fancy, and write this in the same colors as the last slide, only in reverse, so that they match. Okay? So when you see molar volume, it's going to be purple. So we've got 9.21 liters of oxygen gas that needs to be converted to moles of oxygen gas. We use molar volume to do that. Again, that's 1 mole of gas is 22.4 liters. When we start writing our equation, we've got 9.21 liters of oxygen gas, and we need to make that unit equation into a unit factor. We're trying to get rid of liters. So where should I put liters? The top or the bottom? We should put liters at the bottom because we want to get rid of it. So our 22.4 liters is at the bottom. Our 1 mole of oxygen gas is at the top. That's going to get us from liters of oxygen to moles of oxygen. The middle step is always the same because you have moles of one thing and you need to go to moles of another. In this case, we have moles of oxygen and we're trying to get to moles of sodium chlorate. What do we need to go from moles of oxygen to moles of sodium chlorate? What is that called? Mole ratio. Y'all should be giving Cameron all the things. He is holding y'all down right now. We need a mole ratio. It's alright, Cameron's going to get 105 on this next exam because he's getting all the answers this time. So we need to know something about moles of oxygen and something about moles of sodium chlorate. We're trying to get to the number of moles of sodium chlorate that we make. I wish I could give extra credit, but I think homework, you'll do well. If you're getting it now, it'll only sink in better. And we're trying to get to the moles of sodium chlorate. Should moles sodium chlorate go on the top or the bottom? And just as a hint, our sodium chlorate is our unknown. Right. See, this Cameron duo, y'all are it. So we put our 2 moles of sodium chlorate on the top. And if you don't understand, please don't let me just keep going. The class is for everybody. Y'all are here. Unless you want to just put it on and mute me and watch a movie, that's fine. My feelings are just a little bit hurt. But if you want to participate and you want to get it, jump on in. It's okay to be like, Dr. Hefner, run that back. That's really okay. So what we're trying to do is get to moles of sodium chlorate. We put that on the top of our mole ratio. On the bottom, we're going to put 3 moles of oxygen gas, because that is what is in the balanced equation. So what we want to know about goes in the top, the unknown from the balanced equation. What we're given information about already, you take that number of moles from the balanced equation and put it in the bottom. One more step. We've got to go from moles of sodium chlorate to grams of sodium chlorate. What do we need to do that? To go from moles to grams. Molar mass. So I'm not going to make you figure out the molar mass, but you will need to remember how to do that from chapter 8. The molar mass for sodium chlorate is 106.443 grams per mole. Where do my grams go? Top or bottom? Yes. Grams go at the top. And the moles go at the bottom. Put that into your calculator, see what you get. Don't forget to give me units. I think I got 29.2, but I ain't gonna hold you. And always make sure to tell me that grams and grams of what. So that's volume to mass. You take your liters, convert that to moles, take your moles, convert that to moles of your unknown. Then you take the moles of unknown and convert to grams of unknown using molar mass. Now, one thing that you want to make sure of Make sure that your volume, your given volume, is in liters. And that's because the molar volume that we're using, that equality, the 1 mole is equal to 22.4 liters. If you have anything other than liters, then you're not going to be able to do that calculation. So your given volume in a volume to mass problem, make sure that it's in liters. So that's it for today's class. I wanted to leave enough time for people to ask questions. This is your next mini problem set. It's due on Monday by midnight. Monday is 420. I'm old, but I ain't dumb. If you're going to be dumb, don't be stupid. Do your homework before you get high. Okay? So please. I know, Monday is 420. All right? Do your homework before then. There's plenty of time. There's the one that's due tomorrow. Look, I'm real. And that's what people forget. Look, I'm real. Do your homework before Monday. Ain't no shame. I ain't gonna hold you. You ain't my kids. But get it done before then. All right? And whatever you do, please be safe. Please be safe. Oh, yeah, I know. Look, I was a student before, too. And this ain't my first rodeo. So whatever you do, be safe. I would like to see you on Tuesday morning and not have you be a mess. Fair?